Hi, welcome to Napoleon's Theorem by Sarah and Geneva. I hope you guys enjoy. So a fun fact about Napoleon was that in order to create a new class of leaders, Napoleon reorganized France's education system. He started primary schools and created a secondary school system, and although he created separate schools for girls that focused on domestic skills, they are also taught more advanced subjects like mathematics, history, geography, physics, and botany. So Napoleon's theorem states, if equilateral triangles are constructed on the sides of any arbitrary triangle, all outward, the lines connecting the centroids of these equilateral triangles themselves form an equilateral triangle, as you can see here. So some background knowledge that we need is angles and parallel lines, area of a triangle and Pythagorean theorem, similarity, law of sines, law of cosines, properties of equilateral triangles, parallelograms, and the centroid. So looking at angles and parallel lines, looking at this diagram, we know that angle 1 is equal to angle 4, and angle 2 is equal to angle 3. And the reason we can say this is because we know that angle 1 and angle 2 equal 180 degrees. We know that angle 2 and 4 have to equal 180 degrees. We know 4 and 3 have to equal 180 degrees. And we know 3 and 1 have to equal 180 degrees. Now, if we say angle 1 is angle A, then we can say angle 2 is 180 minus A, right? And then if we have 2 and 4, it's basically 180 minus A plus A, which is equal to 180. So now we can say that angle 1 and 4 are equal to each other because they're both angle A. And from this, we can also say that angle 2 and 3 are also equal to each other. Now we have angle 8 is equal to angle 4, and angle 7 is equal to angle 3. And we say this because they are corresponding angles. And then we have angle 5 is equal to angle 4, and angle 6 is equal to angle 3, because these sets are alternate interior angles.
Now we introduce the area of a triangle and the Pythagorean theorem. The formula for the area of a triangle is 1/2 base times height. To see where this formula comes from, imagine taking a right triangle and duplicating it, putting those two triangles together, and having a rectangle as a result, as shown in the top left figure. We know that the area of that entire rectangle is base times height. Thus, each triangle is 1/2 of the area of the rectangle and is 1/2 base times height. As seen in the top middle diagram, we can use that same process with a triangle that isn't a right triangle. We duplicate the triangle, put those two together to form a parallelogram whose area is base times height, and conclude that the area of the original triangle is 1/2 of the area of that parallelogram, or in other words, 1/2 base times height. There is another way to express the area of a triangle, which involves the sign of the angles. We have area equals 1/2 BC sine A, or 1/2 AC sine B, or 1/2 AB sine C. This formula comes from taking the height of any triangle and taking the resulting right triangle, BDA, as shown in the diagram, and using the sine of angle B, which equals opposite over hypotenuse, or H over C, using that expression to conclude that height equals C times sine B, and putting that expression for height in the original formula for area, and you get area equals 1/2 A times C sine B. Now that we know about the area of triangles, we can discuss the Pythagorean theorem. Consider the diagram on the right. We have that the whole shape shown there is a square with 4 sides of lengths A plus B. We also see 4 right triangles in that diagram, the blue triangles, with sides B, A, and side lengths B, A, and C, and that yellow square in the middle with side lengths C. We know the area of that whole figure is the side length times the side length, or A plus B times a plus b, which gives us a squared plus 2ab plus b squared. The area of that entire figure is also equal to the area of the yellow square, which is c squared, and the 4 blue triangles. Each blue triangle has an area of 1/2 a times b. Since they are right triangles, the height is just a. Therefore, the sum of the areas of those 4 triangles is 4 times 1/2 ab, which equals 2ab. We now have 2 expressions for the area of that whole figure, a squared plus 2ab plus b squared, and c squared plus 2ab. We set those expressions equal to each other and are left with a squared plus b squared equals c squared, which is the Pythagorean theorem. The Pythagorean theorem states that in a right triangle, the sum of the squares of the 2 sides is equal to the square of the length of the hypotenuse. Another topic used in the proof of Napoleon's theorem is the similarity of triangles. We say that triangles are similar if they have the same shape but not necessarily the same size. Angles and side lengths determine if 2 triangles are similar. If at least 2 corresponding angles are equal, then the triangles are considered similar. Corresponding means that the side or angle is in the same place in the 2 triangles. So for example, we see that side AB on the left is between the angle A and angle B, and since angle A and angle B are equal and correspond to angle P and angle Q respectively, we know that PQ is the side on the smaller triangle that corresponds to AB on the larger triangle. When we know 2 triangles are similar, we know that the corresponding side lengths are proportional. Therefore, we are left with these ratios, which all equal each other. We also know that taking any 2 sides in the same triangle equals the ratio of those 2 corresponding sides in the smaller triangle. So you say AB over BC equals PQ over QR, for example.
So the law of sine is A divided by sine A equals B divided by sine B is equal to C divided by sine C. And we know that sine A is equal to H divided by C, as shown in the diagram, and we know that C sine A is equal to H. Then we have sine C is equal to H divided by A, and that becomes A sine C is equal to H. Since C sine A is equal to H, and A sine C is also equal to H, we can have them equal each other. So C sine A is equal to A sine C. And if we divide sine C from both sides, we are left with C sine A divided by sine C is equal to A. And if we divide sine A from both sides, we are left with C divided by sine C is equal to A divided by sine A.
Next, we move on to the law of cosines, which states that in any triangle, c squared equals a squared plus b squared minus 2ab cosine c, or a squared equals b squared plus c squared minus 2bc cosine a, or b squared equals a squared plus c squared minus 2ac cosine b. To get these formulas, we draw the height of the triangle, h, and we're left with 2 right triangles, ABD and ADC. Since ADC is a right triangle, we can say that the cosine of angle C equals adjacent over hypotenuse, or DC over AC, which, as labeled in our diagram, is x over b. We rearrange this to get x equals b times cosine C. Since this is a right triangle, we can apply the Pythagorean theorem and say that b squared equals x squared plus h squared. And that c squared on the other right triangle in our diagram equals h squared plus a minus x squared. A minus x is the quantity BD. Now we have c squared equals b squared minus x squared plus a minus x squared. And we get a squared plus b squared minus 2ax. Since we know x equals b times cosine c, we put that into the expression we just found, and we're left with c squared equals a squared plus b squared minus 2ab times cosine c. By the same reasoning, we can get the expression for the other side lengths a and b.
Let's take a look at the properties of equilateral triangles. So we know that all sides of the triangle are equal, and we know that all the angles are equal as well. So 180 divided by 3 is 60 degrees. So all angles are 60 degrees. But an important thing to note is that the median of the triangle is equal to the angle bisector of the triangle. And the median in this case is a line from the vertex to the midpoint of the opposite side, and the angle bisector basically divides the angle of the vertex into two equal angles. So let's look at the proof. Let's draw a line from A to D. So let's look at triangles ACD and ADB. We have, if AD was the median of the triangle, then CD is equal to BD, because AD divides the side CB into two equal sides. And then we have angle C is equal to angle B because it is given, and we know that AC is equal to AB because it is given. So by SAS congruence, triangle ACD is congruent to triangle ADB. Now, if we say that AD was the angle bisector of the triangle, then we know that angle CAD is equal to angle DAB, and we know that AD is equal to AD because they're the same line, and we know that AC is equal to AB because it is given. So again, by SAS congruence, we can say triangle ACD is congruent to triangle ADB. And from this, we can tell that the median of the triangle is also equal to the angle bisector of the triangle.
Now we will talk about parallelograms. The definition of a parallelogram is a quadrilateral ABCD with AB parallel to CD and AD parallel to BC. In other words, a parallelogram is a four-sided figure in which the opposite sides are parallel to each other. We know a theorem about parallelograms which states, in quadrilateral ABCD, suppose that AB equals CD and AB is parallel to CD. Then ABCD is a parallelogram. The proof of this theorem involves triangles. As you can see in the figure, we are given that AB is parallel to CD, so we know that the alternate interior angles, BAC and ACD, are equal. We also know that AB equals CD, and we know that side AC is equal to itself. We can conclude that those two triangles that form the parallelogram are congruent by the side-angle-side criterion. Since angles CAD and ACB are corresponding angles of congruent triangles, they are equal. Since alternate interior angles CAD and ACB are equal, AD is parallel to BC. Now we know that we are given that AB is parallel to CD, and we found out that AD is parallel to BC. Thus, our figure is a parallelogram. We now introduce a theorem that we will use to develop theorems about the centroid later. This theorem states, let U and V be points on sides CA and CB of triangle ABC, as shown in the diagram. Then UV is parallel to BC if and only if AU over AB equals AV over AC. The proof of this theorem involves a lot of steps, and in the interest of time and focusing on Napoleon's theorem, feel free to pause on any slide to study the equations and substitutions we use, but I will be going relatively quickly through each step so that we can get to the main proof. We start by establishing expressions for alpha and beta. We then do some rearranging of expressions for the side lengths to come up with these expressions, which state AU equals 1 minus alpha times AB, and AV equals 1 minus beta times AC. Rearranging the equations from the previous slide, we get that AU over AB equals 1 minus alpha, and AV over AC equals 1 minus beta. We know that these ratios equal each other if and only if alpha equals beta. So now our goal for the proof is to show that alpha equals beta if and only if UV is parallel to BC, which is the goal of the proof. For the next portion of the proof, we draw a few more lines in order to further our analysis. We look at the area of triangle BUC compared with the area of triangle ABC. The important thing to point out in this slide is that the height of triangle BUC with respect to base BU is the same as the height of triangle ABC with AB as the base. That is all the background knowledge you need to understand where the equations on this slide come from. If we repeat the process shown on the previous slide with triangle BVC instead, we get a similar expression for the area of BVC, which is beta times the area of the larger triangle ABC. Now that we have these expressions, we know that alpha and beta are equal if and only if the area of triangle BUC equals the area of triangle BVC. Now, in order to prove the original theorem, we need to show that the area of those two triangles are equal if and only if UV is parallel to BC. The conclusion of this proof involves analyzing the areas of triangles BUC and BVC and using the properties of parallelograms that we previously discussed. Feel free to pause on this slide and read through the proof in detail if you would like. We now introduce the centroid, which is the point at which the medians of a triangle concur. Remember that the median of a triangle is the line from a vertex to the midpoint of the side opposite to that vertex. To prove some properties about the centroid, we will begin with this proof. Consider the triangle ABC with medians AX and BY drawn in. Recall, XY is parallel to AB if and only if CY over CA equals CX over CB. That was the theorem with the long and involved proof that we just discussed. Since we know y is the midpoint of CA, CY over CA equals 1/2 CA over CA, which equals 1/2. Similarly, since x is the midpoint of BC, CX over CB equals 1/2. Thus, CY over CA equals CX over CB, which equals 1/2, and we can say that XY is parallel to AB. We now have the same diagram, but with some lines removed for simplicity. We have established that XY is parallel to AB. Now consider the triangles CYX and ABC. Since XY is parallel to AB, corresponding angles BAY and XYC are equal, as shown in the diagram. Angle YCX equals itself. Thus, the triangles are similar by the angle-angle criterion. Since y is the midpoint, we know that CY equals 1/2 CA, so the ratio of the sides is 1 to 2 in these similar triangles. Thus, XY equals 1/2 the corresponding side, which is AB. We reintroduce the medians to the diagram. We know that the alternate interior angles BAO and YXO are equal since XY is parallel to AB. We also know that vertical angles BOA and YOX are equal. Thus, triangles BAO and YXO are similar by angle-angle. We previously established that YX was 1/2 AB because this is still the same diagram we've been working with. Therefore, for corresponding sides YO and BO, YO equals 1/2 BO. Similarly, XO equals 1/2 AO. Therefore, point O, which is the centroid because it's where two medians intersect, lies 2/3 of the way from A to X and 2/3 of the way from B to Y. If we take the same triangle, but now introduce median CW and the previous median AX, we can do a repetition of the proof we just did with AX and BY, and do it with AX and CW, and show that CW intersects A at a point 2/3 of the way from A to X. Since there is only one point that is 2/3 of the way from A to X, CW must intersect AX, and thus also BY, at point O. Therefore, we have established that the medians of a triangle are concurrent at a point that is 2/3 of the way from each vertex to its opposite side.
Okay, so now that we have all the background knowledge that we need, let's work on the proof. Taking a look at this diagram, we have angle IAC is equal to angle GAB, which is equal to 30 degrees. Applying the law of cosines, we get s squared equals u squared plus t squared minus 2ut times cosine A plus 60 degrees. This is equation 1. Using what we know about the centroid, we can see that t is equal to 2/3 times square root 3/2 times c, which is simplified to c divided by square root 3, And we have u is equal to 2/3 times square root 3 over 2 times b, which simplifies to b over square root 3. And then we plug this information into equation 1, and we can simplify it to get 3s squared equals b squared plus c squared minus 2bc times cosine a plus 60. You may pause to look at the work. So using the cosine additive identity and recalling that cosine 60 degrees equals half and sine 60 degrees equals square root 3 over 2, we have cosine a plus 60 degrees is equal to half cosine a minus square root 3 over 2 sine a. We plug this into equation 2 and simplify it to get 3s squared equals b squared plus c squared minus bc cosine a plus square root 3 bc sine a. So that is equation 3. Now applying the law of cosines to triangle ABC, we get a squared equals b squared plus c squared minus 2bc times cosine a. So we bring b squared plus c squared to the other side, so we get a squared minus b squared minus c squared equals negative 2bc times cosine a. And we bring the we bring 2 to the other side, so we have half a squared minus b squared minus c squared equals negative bc times cosine a. Also recall that 2 times the area of triangle ABC is equal to BC times sine A. So we plug all this information that we get and we plug it into equation 3 and we simplify it to get s squared is equal to 1/6 a squared plus b squared plus c squared plus 2 square root 3 over 3 times the area of triangle ABC. And then by symmetry, we can say that S is equal to GI is equal to GH is equal to HI, proving that triangle GHI is an equilateral triangle. I hope you guys enjoy this proof, and I hope you guys learned something from it. Thank you so much.